Welcome to the morning session. Our first speaker is Ivan Kenlaya from UC San Diego. He will talk about some applications of field theory to the measure of Euclidean varieties.
All right, thank you. I'd like to thank the organizers for the opportunity to speak. So during the pre-talk, I recorded some notation, which I will review in a moment. But first, let me state what the premise of this talk is, what the goal is. So I want to sort of explain three things, not in this order, but this is sort of natural order in which to state the goals of this talk. So I want to answer first the question, what is the Galois group of an abelian variety? And the second question is, what can we say about it? And the third question, which is what the one I'll answer first, is why should we care? So I hope to indicate all three of these things over the course of the talk. So before I proceed to explain the answer to this question initially, let me recall the notation that I'll be using. So throughout this talk, K is going to denote a number field. So your favorite, that's the white chalk. So your favorite finite extension of the rational numbers, I'll switch to the white chalk, because I think it'll show up better, but it's probably fine for now. So K will be a number field, and G sub K will always denote the absolute Galois group. So I'll fix an algebraic closure of K, and GK will denote the automorphism of that algebraic closure. A will always denote an abelian variety over K of some dimension. I'll rule out the case of the zero abelian variety, just in case Sarah's hiding in the corner somewhere. So G will denote the dimension, and I call it G, of course, because I have the example in my head of A being the Jacobian of a curve of genus G. But I'm not assuming that A is a Jacobian, or even that A is principally polarized. So, of course, E is you should think of the example of an elliptic curve. I'll come back to this in a moment. But first, let me mention that if L is your favorite prime number, I'm going to write TL for the integral Tate module of A. So that's this inverse limit of L power torsion points over the algebraic closure of K. So that's some free ZL module of rank 2G with an action of GK. It's actually a continuous action for the appropriate topology of this thing. And VL will be the analogous thing where instead of a ZL module, I just formally extend it to a QL vector space. Okay. Right, so let me come back to this line. So throughout the talk, we're going to see the trichotomy between three types of elliptic curves. And this notion of a Galois group is really going to help us sort of sort out, in the general case, what the correct analog of this trichotomy is. So the trichotomy is that some elliptic curves have complex multiplication, and some don't. But of the ones that have complex multiplication, the endomorphisms may live over the original field K over some larger field. So for example, if you think about an elliptic curve with an automorphism, you can write down an elliptic curve. Maybe I shouldn't have erased this one. So I had this on the board during the pre-talk. So this elliptic curve, y squared equals x cubed minus x, is special because it has an automorphism of order 4. X goes to minus x, y goes to square root of minus 1 times y. So, but this elliptic curve is realized over the rational numbers, but the endomorphism requires a larger field to write it down. So that's a case of CM not over the base field. Whereas if I were working over, if I had written this down and viewed it as an abelian variety over a field containing the square root of minus 1, then it would be in this case. So the only difference between these two cases is fields of definition. Really, so geometrically, the main distinction is between these two. But since my talk is about arithmetic, not just geometry, I want to actually keep track of this arithmetic distinction as well.
John?
Yes?
Next time you write, can you write bigger?
Yes, I will switch to the white chalk and write bigger. Yeah, the thick chalk that didn't erase had the feature that it was more visible, so I guess I have to compensate with the bigger handwriting. so let's test this out on my newly clean board over here. Okay, so the question of why should we care, I will answer with 3 different components, and I've indicated those over here. Let me spell them out in more detail. So one question that can be that receives information from the Galois group, which I haven't defined yet, is the question of where do endomorphisms of a given abelian variety live. So I didn't write this. So I'm going to write end of A to be the ring of endomorphisms of A. So this is not a ring in the commutative sense necessarily, but it is some. So this is some finite, free, not necessarily commutative Z algebra. And I'm going to distinguish in my notation between endomorphisms of A, meaning A as an abelian variety over K, and endomorphisms of A base change to an algebraic closure. So when I write this, I really mean only the endomorphisms that are actually defined over K, and here I mean the ones that you can find over K bar. Do I need to write even bigger than this? Even bigger than this. Okay. Let's test this out. Okay, so. Better? Excellent. Okay, I will. If my font size, if I get smaller, just like do this. Okay, so I'm going to distinguish between the endomorphism ring of A itself and A over an algebraic closure. And in particular, I'm interested in the question, well, maybe I should sort of state a proposition. Proposition bigger than this? Okay. There is a unique, minimal, and it also happens to be a finite extension, so it's actually a number field. I'll call it L throughout the talk, of K, such that all the endomorphisms of A that are defined over L constitute all of the endomorphisms of A that are defined over an algebraically closed field. So I'll say this out loud as all the endomorphisms of A are realized over L. But really, I mean all the endomorphisms of A over an algebraically closed field are actually realized over this particular finite extension. So this is not hard to check. And in particular, this turns out to be a finite and Galois extension. And so the question I want to ask is, well, how big can this be? So, for example, for G equals 1, either L equals K or L over K is a quadratic extension. Because I can just look at this trichotomy. In this case, L equals K. In this case, L equals K. And in this case, we know that you have to make a quadratic extension. So one of the questions one would like to answer is, well, how big, for example, how big can the degree of this extension be? What can the Galois group look like? And maybe even what groups can actually occur. So for G equals 2, these questions are all answered by some So I have a paper with Francesc Futet, who's here, Victor Rocher, and Andrew Sutherland, who is also here. You'll recognize his handiwork on the slides. So we can answer this question in the case G equals 2. And the answer, actually I can say it this way, is that this degree can be a little bit bigger. It always divides 48, and this bound is sharp in the sense that 48 is actually achieved. And this bound is achieved. I should point out that there's two different ways in which this bound could be sharp, right? Because it could be that 48 is the smallest number that has the property that these degrees always divide 48. But that doesn't mean that you can actually find an example with 48. It could be that you can find an example with 16 and an example with 6, but you can't find anything bigger. That would still force you to take 48 here, because that's the LCM. But it turns out in this case that actually there is, you actually can construct a few examples with 48. And in this case, if I remember correctly, the Galois group is, in this case, is S4 times Z mod 2Z. Question?
Is it sharp in the sense that every divisor of 48 appears?
Yes, because, yes. Yeah, that's not a priori true, but it is true from the statement of the theorem that we have examples for all of the divisors of 48. Yeah, you wouldn't normally expect that. So if you start proving theorems about higher genera, maybe I'll just jump ahead to this point. When you get to higher genera, the bound that you're going to be able to get is almost certainly not going to be achieved, and you don't expect necessarily divisors of an order that you see to be forced to appear. But it sort of depends on group theory.
Doesn't it depend on K also?
Yes, of course. So this bound is achieved for certain K. So I'm stating this in a manner that sort of doesn't privilege a choice of K. Yes, if you make certain choices for K, then you lose possibilities, like we already saw for elliptic group. So we'll see later that there are some, you can kind of classify the possibilities, and many of them don't occur when K equals Q. But that's better to state in the full context of Galois groups. Come back to that. Okay. So one of the questions we'd like to answer is, what can I say when G is bigger than 2? And we have some partial results, but I'll come back to those at the end of the video. Okay. So the second instance of why should we care about doing Galois theory for abelian varieties is, since you may not be able to see it, it says Galois images. So I talked about the Tate module briefly. So this is a big question in the arithmetic of already for elliptic curves is how big can the image, so say for A in elliptic curve, you have this map from GK into, well, you have an action of GK on the Tate module for your favorite prime L, so that gives you some map from the GK into the group of, well, in this case G is 1, so 2 by 2 invertible matrices over ZL, and you can ask, well, how big is the image? Well, that depends on this arithmetic distinction. So if E is not CM, then this image is quite large. This image is an open subgroup. It actually has finite index in this. And I'm tempted to say this is due to Serre. That's the oldest reference I can think of. I hope that is in fact correct. Right, so Serre has a whole book about this topic. But if it's CM, then actually the group is the image is much smaller. And in some sense, that's not surprising, because why is it smaller? Well, Galois has to, so GK must sort of behave nicely with respect to endomorphisms. So in the case where E has no complex multiplication, the only endomorphisms of E are multiplication by integers, so there are no apparent constraints on how the action of Galois sits inside here. But when you have endomorphisms, right, those things, since endomorphisms are defined over some number field, the absolute Galois group of K acts on them. So the point is that, this is somehow the point, that if you take the endomorphisms of A over K bar, A is E in this example, but this is true in general, that GK acts on them because these things are written down using coefficients in some number field, some extension of K, and GK moves those coordinates around. So GK acts, so these things are geometric structures, so GK acts on them, and on the other hand, these things act on torsion points, so the action of GK on torsion points has to somehow interact with the action of these. So for example, if you have some endomorphism which is actually defined over the base field, then GK has to commute with it. And if it's not defined over the base field, then there's some slightly twisted version of that statement. We'll see this. I'll make a definition that takes advantage of this in a moment. But so you can try to ask, well, how big should the Galois image be for general A? And clearly, you see the answer. In order to even hope to answer that question, you have to straighten out what geometric constraints there are that would be keeping you from having an image as large as you would expect. So that's the second reason why you need to understand the Galois theory of abelian variety in order to say something about its arithmetic. And the third topic is problems of equidistribution. So, for example, if E is an elliptic curve, so if E is defined over the rational numbers, say, then you can clear denominators, and then for most primes, meaning all but finitely many of them, you can sort of form a reduction. Say if E is defined over Q, then for almost all P, you can reduce modulo P to get an elliptic curve over a finite field. Right? Really what you need to do is take a model of this over the integers, and then take the base extension to FP, and for finitely many primes, possibly depending on your model, you get something which is not an elliptic curve because it's not smooth anymore, but you just throw those out. And this thing, of course, has a finite number of points. So this is really what Kristen was using in her talk yesterday. So she was really interested in, well, take an elliptic curve over a finite field, and then the group of points, maybe I'll lighten the notation and just call this E. This isn't literally valid because, of course, there's no basic section from here to here, but pretend that I went through the integers. Okay, so if I take the number of points on E over this finite field FP, this is, of course, a finite number, and you can say more than that. It has a form P plus 1 minus AP, where by the theorem of Hasse, this is in fact not as big as P, it's only as big as 2 times the square root of P in absolute value. So it's close to P plus 1. And you can ask, well, if I take this number, AP divided by the square root of P, that belongs in the interval from -2 to +2. So now I have a sequence of different points in this interval, and I can ask, well, how are they distributed? Well, so if you want to state this mathematically, what you would do is you would look for some measure on this interval such that if you take the moving average of the point measures corresponding to these points, that converges weakly in measure to the measure on here, meaning that if you test any continuous function by sampling its values at these points and taking the moving average, you converge to the interval of that function over here. Yes?
Are you fixing the curve there in P, or are you fixing P?
I'm fixing an elliptic curve invariant P. That's a good question. So fix P. You can ask these questions where you fix P invariant E, but they're much easier. And they have sort of similar answers, but I won't get into that. So I'm imagining a situation where you fix at E, or in general an abelian variety, and you look at sort of information about the reductions over finite fields. So in this case, I just want to look at the number of points, FP rational points, on this thing. Now, if I were to find over a number field, I would reduce modulo prime ideal and do the same thing. But in some sense, most primes in a number field have absolute degree 1. So this situation is actually reasonable. Okay, so I told you what the mathematical way is to ask this question about how these points spread out. It's some measure theoretic statement. But the more concrete thing to do is actually just sort of make histogram plots. So this is what Drew did in these 3 examples. So this data was pre-computed, but it's being shown in an animated fashion on the 2 sideboards. So you take the curve y squared equals x cubed plus x plus 1, which does not have complex multiplication, and you take this function, you take this quantity AP over square root of p, and you make some sort of histogram plot where the granularity is increasing with the number of sample points, so you get some reasonably smooth picture. And you see what happens as you take more sample points. And it's a little bit hard to see, and I apologize. I haven't figured out how to make it bigger on this browser. But this is samples up to p equals 2 to the 40, which is an awful lot of samples. It's an interesting story how you get that many samples. If you were at the ISIM workshop this past week, you may have heard about this, but I won't go into it. Just suffice to say, there's interesting mathematics, which is orthogonal to this talk, related to how you get these samples. The point I want to make is that you see an interesting semicircular graph here. So in fact, the distribution that this thing is trying to converge to is given by exactly the semicircular graph that you would interpolate here. And the amazing thing
So is the little stem we see there an artifact?
That's an artifact. Yeah, that's an artifact. It has to do with the granularity of the plot. But so the amazing thing that happens, and this was observed numerically by Sato something like almost 50 years ago, with of course much less data, because it was computers in the 1960s that were doing the computation. And Tate had some more theoretical reason to think this. But it turns out that whenever you take an elliptic curve without complex multiplication, you expect, over any number field, you expect to see this picture. So this trichotomy, this part of the trichotomy gives you only one picture, no matter which elliptic curve you take. So you fix any elliptic curve, you do the same thing, you get the same picture. So Drew has another example on his webpage that I like to point out. So you could try this with, for example, the example of Elke's of a curve which is known to have 28 independent rational points. And there, the picture starts out being very skewed for reasons that you might enjoy trying to figure out. But it still converges eventually back to the same picture. You get the same circular graph. The moments along the bottom, these are expected values of the powers of this random variable. In case you recognize them, you might see if you can figure out which interpretation of them I'm using. We'll see that. We'll see a little bit later. And I should mention that these other two cases look very different. But again, each one of them corresponds to only one picture. So if I take a curve with complex multiplication over the field of definition and do the analogous calculation, I always get a picture that has the same limiting shape as this one. So it looks like the function is diverging, but its integral is proper. So this is still a well-defined distribution.
There's a question over there.
There's a question over here. Yes?
So it occurs to me to ask, looking at this picture you just showed us of Elke's curve with rank 28, now that lots of smart people think that the Mordell-Van rank of an elliptic curve over Q might be absolutely bounded independent of the curve, do you does your data suggest that the speed of convergence to the solid tape distribution might be, that the sort of the error term might be bounded uniformly at the height of the curve?
If we knew that ranks were bounded and we knew BSD, then that would give some information, uniform information about the rate of convergence. Because the rate of convergence has to do with, so aside for the arithmetically minded people in the room, the rate of convergence, the convergence as this picture is related to the analytic behavior of certain L functions. In particular, especially the L function associated to the elliptic curve. Also the symmetric powers, but the L function associated to the elliptic curve is the one that contributes the main term, and that has to do with the order of the singularity at s equals 1, which is, of course, under BSD, the rank of the Mordell-Weil group. So the higher the pole there, which comes from more rank, the more sort of logarithmic main terms you have to strip off before you see the error term that corresponds to the Riemann hypothesis. So yeah, if you knew boundedness of ranks, that would give you some uniform control over the convergent situation, uniform over elliptic curves. But you would have to know a lot of other things too, like the Riemann hypothesis for these L functions. Or at least some zero-free region. Anyway. Yeah, I should maybe end that discussion by saying, I'm going to say very little about, since this is an algebraic geometry conference, not a number theory conference, I'm not going to say much more than what I just said about how you would actually prove that these pictures actually converge to what they do. As I said, it has to do with the analytic continuation properties of certain L functions. Those are in general very hard to establish. They use the kitchen sink of modern number theory to do as much as we can. And then some of the pictures I'll show later, modern number theory throws up its hands and gives up. So the questions that I'm implicitly posing by showing the pictures here are actually very, very hard in some cases. And some of them are so hard that we don't hope to solve them possibly, in our lifetimes. But at least we can figure out empirically what the right guess is and correlate it to some actual structure, which is the Galois group of Nebelian variety, which I'll talk about. Okay, so there was one other picture that I wanted to show before we move on, which is the analogous picture. In this case, if you have an elliptic curve with complex multiplication not defined over K, then you always get convergence to a picture that looks like this. So the curve you're seeing here is the same graph that I had before multiplied by 1/2, but now you're seeing something else. You're seeing something in the middle here, which is not an artifact. This is a discrete measure concentrated at 0 of total measure 1/2. So that's why it's spiking here, because when you try to graph a Dirac delta function, that's what happens. Why am I seeing that in here? Well, there's a very good arithmetic reason. So if you take, for example, this thing, you get AP equals 0 whenever P is 3 mod 4. So in this example, if P is 3 mod 4, you always get AP equals 0. And that was already observed, I think, by Gauss. Or maybe for the other famous example, y squared equals x cubed minus 1. So this kind of thing was observed by Gauss, where you take the convex 1, 6. But so sort of half the time you're forced to see AP equals 0, and so if you want to explain these pictures in terms of some sort of Galois theory for abelian varieties, that explanation had better include an explanation for this discrete component of the measure. Yes, Dan?
Is half the time always how P splits in the CM field?
Well, in this case, in the case of elliptic curves, the extension you have to go to is always quadratic, and so it really is a half and half. I'll show you more pictures later. I will make sure to leave time to show you more pictures later, where the fractions are not half and half. They can be much more exotic. But so for genus 1, it's always half and half.
But this is about splitting, right?
This has to do with splitting of the prime in a quadratic extension. And in general, it will have to do something with splitting in some extension, but it'll be more some complicated extension. Like it could be it's actually going to be in this extension. So it could be an extension with this Galois group, which is a little bit more complicated. Okay, I suppose I can leave the pictures up while I continue. So let's start doing some mathematics now. Let's talk about what I mean what I want to mean by the Galois group of an abelian variety. So maybe I'll erase this stuff. We'll test this chart now. Oh, this chart does erase. Okay, so now let me introduce, in a very gentle way, the concept of a motivic Galois group associated to an abelian variety. In particular, I won't say much about the word motive hiding in this name. I'll have to mention it at some point, just in passing, but I'll tell you as much as I can about this without having to say what a motive is. This definition was originally written down by Serre in a slightly inexplicit way. So the way I'm going to think about it for the purposes of this talk was written down by myself and Grzegorz Banaszak a couple of years ago. But really, the content of this definition is due to Serre, so I don't want to misallocate credit here. This is just sort of interpreting what Serre said in a way that we could apply. Okay, so for the purposes of this definition, I will do something slightly uncanonical, which is I'm going to fix an embedding of k into the complex numbers. I mean, this is not like fixing an embedding of k bar into the complex numbers, but if k is imaginary quadratic, for example, or real quadratic, there's some choice I'm making, but it's not a. It turns out it doesn't really affect the definitions, but it's much easier to explain them if I make this choice first. So let's do that. Okay, so if I've embedded k into the complex numbers in some fashion, and actually maybe I will go ahead and think of the k bar that I have in mind as the one that sits inside the complex numbers. Nothing I've really said depends on which algebraic closure I'm taking. So if I put k inside C, let me just take the algebraic closure inside C. Which will have lots of automorphisms that don't come from C, but for definiteness. Okay, so now since I have an abelian variety over a field which is sitting inside the complex numbers, I can base extend it to the complex numbers. And now this thing is an algebraic variety, but it has an underlying complex analytic space, and in particular an underlying topological space. So I'll write superscript and for, or maybe I should write superscript top for the underlying topological space. So this means underlying topological space. I guess my handwriting gets bigger, but it doesn't necessarily get neater. I apologize. I hope it's still manageable. Okay, so this is a topological space, so I can take singular homology with rational coefficients. So let me call this space V. Okay, so this is a 2D dimensional rational vector space. It has some extra structure, which we haven't really talked about much yet, but was sort of hiding in all of the background here. This has a non-trivial symplectic pairing, symplectic, or if we want alternating, which I'll call psi. And this comes from, say, the cup product in singular homology. If you're thinking in terms of Étale cohomology or Tate modules, you're seeing essentially the same thing in the context of the Weil pairing. So we'll see the Weil pairing again in a moment. In this world of simplicial, or say singular homology, it's a negative product. Well, maybe it's, I'm going to gloss over where this thing actually comes from. It has to do with if you think really in terms of kind of the analytic theory of complex tori, it has to do with the polarization, or the Riemann form. Okay, so why does this have to do with the arithmetic? Well, it's not immediately obvious what it has to do with the arithmetic, because I went and did something topological. So in particular, the Galois group GK does not act on V in any natural way. However, there are some related things. So the endomorphisms of A defined over K bar do act on V. Because any endomorphism of A as an algebraic variety of the complex numbers will act on this homology. And GK acts on this algebra of endomorphisms. So I can put that information together in the following way. And I'm going to write this for, this will be, so to speak, the naive motivic Galois group. Naive because it's not quite the right answer in general, but it's a good working definition for starters. So this is going to be a subgroup of, so I'm going to take the linear endomorphisms, linear automorphisms of V that respect the symplectic form. That's SP of V complex psi. So this is some linear group defined over Q, and I'm going to take the subgroup, well, it's really the subgroup variety, but I'll tell you how to characterize it on the level of points. So it has the property that I'll write G inverse end of AK. So the action of G, let me say it this way, G acting on endomorphism coincides, no, sorry, I do want the conjugation, because, so I'm going to view the endomorphisms as mapping into this group, and I'm going to look at elements with the property, G with the property that if you conjugate any endomorphism by this action of G, it would be the same thing as applying a certain element of the Galois group. Which depends only on G. So the action of G on the entire endomorphism algebra coincides with the action of some, let me put this up here so I can write it more clearly. So there's some element of the Galois group depending on K, such that the action of tau on the endomorphism algebra is, so this thing must in particular normalize, it must stabilize the endomorphism algebra, and it acts on it as some element of the Galois group. I mean the action of tau on, let me write this out more carefully so we can see what it means. So I mean, for all, say, H in endomorphisms of A K bar, but I'm implicitly going to view H as acting on V. So G inverse, so there exists some tau depending purely on G, such that, the conjugation of H by G belongs again to this subset of SPA and is also computed by this element of tau applied to H. So this is somehow the key definition here, so we should spend maybe a few extra moments making sure that we all understand what I'm talking about. So, right, a general element of SP will not send, right, if I map this thing into, well, not SP, sorry, because this is a group and these elements are not necessarily invertible. So if I take these things, they act on V, preserving the symplectic structure. So this is some subring, some algebra of the matrix ring, so the fun morphism ring of V over Q. Okay? And inside that, I want to have this kind of equality. I want to know that for G, there corresponds some element of Galois such that when you conjugate every endomorphism by G, you get the thing that looks like the linear action of some endomorphism, and which endomorphism? The one that you get by hitting H with this element of Galois. So in particular, this includes things that are, this includes elements of G that fix this endomorphism ring, but I also want to keep track of the ones that move it around in some arithmetically important way. Was there a question? Yes?
I was just wondering, how does the endomorphism act on V?
How does an endomorphism act on V? Well, the point is it acts on this, endomorphisms act on this algebraic variety. So an endomorphism gives me a map from this thing to itself.
Are you only using the anti structure?
Well, I can compose endomorphisms, and then I compose the corresponding. Yeah, but right now for this statement I'm only using. I'm just using the fact that endomorphisms give me maps from V to itself. Yeah, I'm not really using the ring structure on this endomorphism just at the moment. It of course has some effect on what the possibilities are. But okay, so this is somehow the key construction. I'll come back to why it's a bit too naive in a moment, but first let me point out that what kind of object do I get here? So I'm really thinking of this thing as a Q algebraic subgroup of this symplectic group. It's not just defined over Q. I should also say it has dense Q rational points. But that's not the same thing. You can define a group variety over the rational numbers without it having very many Q rational points. Just think about the scheme of, the n torsion of the multiplicative group, where n is bigger than 2. That's a variety defined over the rational numbers, but it doesn't have very many Q rational points. Just 1 and minus 1 if n is even. So this is not that situation. This is a group which is actually not only defined over Q, but actually is the Zariski closure of its set of Q rational points. So you really can think of it as a group of points in, say, the endomorphisms of this thing. Instead of viewing this as a group variety, you can think Q rational points. Let's see, what else can I say about it? It's not necessarily. Now, remember, algebraic groups are not necessarily connected. I just mentioned an example. So if I write this circle to mean the connected part, so the connected part will be some algebraic subgroup, and then the quotient will be some finite, it's some finite group variety, but it's full of Q rational points, so I can really pretend it's just a finite group. And what finite group is it? Well, you could sort of identify it from the description. It's just the Galois group of L over K, where L is the minimal field of definition of endomorphisms. So this Galois group now is showing up as the group of components of some algebraic group. And this is an incredibly useful way to get structural information about this group. So the theorem that I proved earlier uses this interpretation of the Galois group in order to control it. And so we're going to get information about this group, ultimately, by controlling certain algebraic groups defined over Q. Okay. So let me just pay my debt to my sponsor and explain that this construction is not quite the correct construction in general. So warning. So you need to replace the motivic Galois group by some more complicated construction. Using what are called absolute Hodge cycles. So what do I mean? So endomorphisms are sort of the simplest possible algebraic structure you can see on a abelian variety, and one way to see them is you can kind of see them inside. You can sort of relate endomorphisms to codimension 1 cycles. So if you want, elements of H2 that look like that satisfy the Hodge conjecture or the Tate conjecture, whichever version of that you want. Now there are also, in general, algebraic cycles of higher codimension that don't somehow come from the codimension 1 cycles in any obvious way. This was discovered by Mumford. The first case where this can happen is where G equals 4. So if G is at most 3, which it will be in most of the examples that I'm thinking of, we won't see the distinction between the naive construction and the correct construction. But as soon as G is at least 4, you can have cases where, for instance, the naive construction gives you the full symplectic group, but the next thing I'm about to say would fail unless I took a corrected construction. So what is the next thing I'm going to say? The next thing I'm going to say is that Galois images are controlled conjecturally by the correct version of this motivic Galois group. So this is essentially the Mumford-Tate conjecture. So it's some sort of strong generalization of the Serre open image statement from earlier, which is that so if you take the map from GK to GL 2G over QL by the Tate module, you get the image is open in a certain group derived from M. So you take M, take QL points, but now I have to add scalars. And somehow the reason I have to add scalars is if you think about the case of an elliptic curve, right? The Weil pairing on an elliptic curve, right? So reminder, the scalars come from the fact that Weil pairing sort of goes from A, L to the M, times A, L to the M, to the canonical place to put the target is the L to the M portion of the multiplicative group, and this is moved non-trivially by the Galois group of K. So the analogous pairing that you have in the Tate module situation is not actually respected by the Galois group, but it's only respected up to scalars. So you get these extra scalars in here. So for example, when G equals 1, the generic situation is, well, the symplectic group of rank 2 is just a special linear group. When you throw in scalars, you get the whole GL. But for example, when G is 2, there's a difference between the general symplectic group and the full general linear. Those are no longer the same. So already this is saying something not quite obvious when G is bigger than 1, even in sort of the case where this group is as big as it could possibly be, namely the full symplectic group. And so this conjecture is quite challenging. There are a lot of cases of it that are known, but most of the cases that are known are the cases when the group is somehow really big. Maybe when it's the full symplectic group, or at least when it's as big as the naive group, right? Because this group is defined using more conditions, the correct motivic Galois group, it's in general smaller than the naive one. But in many cases, for example, when G is less than 4, they actually coincide, and in those cases, one can actually prove this using known methods. But the cases where they don't coincide, starting with G equals 4, turn out to be quite challenging, and I don't know how much is known about it, but it's not a lot. That having been said, it's much more tractable than the kind of problems that I was pointing to on the slides. Okay. Okay, so I have a couple of minutes, so let me do 2 last things. One is I want to show you some more pictures. So one thing so I've talked about the effect of this motivic Galois group on field of definition. I stated the theorem for G equals 2. I might come back to it if I have a minute or 2 at the end and talk about larger G. Let me show you some pictures of how the motivic Galois group affects equidistribution. So let me write on this backboard here. So the sort of equidistribution. So the analog of taking an elliptic curve, reducing modulo P and counting points is you sort of take A, you reduce it modulo a prime ideal of the number field, and then you look at the characteristic polynomial of Frobenius. Or for those of you who are spending the semester at ICERM, this is the Euler factor of the associated L function. And you look at how that varies as you vary the prime P, and for instance, you can look at, there are various, this is sort of more than one number's worth of information, so to visualize it, you kind of take a single function of this characteristic polynomial, like one of its coefficients, and look at how that varies. But really you prove theorems about the joint distribution of this. And so, for example, if you're in a situation, say, where G equals 2, and this motivic Galois group is the maximum possible, then the first coefficient of the characteristic polynomial, appropriately normalized, will distribute according to this kind of picture. And again, the expected values of the powers are certain integers that have some explicit meaning from the point of view of representation theory. So what this picture is actually doing, I should maybe say, this is according to, so the measure that you're supposed to take here on the space of characteristic polynomials. So you're supposed to think of these characteristic polynomials as coming from a certain compact Lie group, which we like to call the Sato-Tate group of A, because it's a formula to generalize the Sato-Tate conjecture for elliptic curves. And this is derived from the motivic Galois group. It's essentially you take the motivic Galois group over R, and you take a maximal compact subgroup inside that. So in this case, you would get the unitary symplectic group when you do this. Maybe I really want to M over. No, it depends on M over R.
So you mean you look at the coefficient of the characteristic polynomial of a random.
You take a random matrix in this compact Lie group, and its characteristic polynomial will have the right statistics. If you plot statistics for that characteristic polynomial, you'll get the same statistics as you will for this. Now, this is highly conjectural. This kind of statement is outside the reach of modern number theory, but nonetheless, you can make the conjecture and test it, and it looks good. However, in this case, the trichotomy that I started with is a little more complicated. So what we proved other three authors I mentioned is that there are exactly 51 exceptional cases. So instead of 3, there are 52. I was thinking of getting a deck of playing cards made where the USB 4 is the ace of spades. Too soon? But yeah, so if you go to Drew's website at MIT, you can see a catalog of these things. And so you can pick, for instance, a super exotic one. If I remember correctly, the J of O. This is the case where the component group has order 48. So here you get all sorts of weird features of the distribution. The spike in here, I don't remember what the measure of the spike is. Is it like 19/24 or something? It's a pretty strange fraction. These are not actual spikes, if I remember correctly. This is just, these are proper integrals. But this is actually a spike of positive measure. It gets even weirder if you look at the A2 coefficient. That's no longer got a forced symmetry. So this has spikes at, these are integers. I don't remember which integers these are like -2 through +4 or something.
-2 to +2.
-2 to +2 are giving you positive measure components. So there's all sorts of weird stuff going on in here, and this 51, which is a little bit illegible, comes from a pure group theoretic classification, well, plus some matching to the arithmetic revealing varieties, in surfaces especially. So this is the kind of thing this is the kind of statement, and the consequence that I mentioned earlier about components is something you really get by, not purely by studying abelian varieties, but matching that with group theory in a very essential way. And I'm running short on time. I want to make one last statement, which is sort of the newest thing that I know in this area. And I'll be really brief. Just mention what we're trying to prove. So, very recently with Bob Grolnick, we've been trying to get better bounds on this degree of the field of endomorphisms by controlling the component groups of this motivic Galois group. So there's an older result of Silverberg, which gives a formula, which gives an upper bound of the form some product of primes. And this thing is where I can tell you explicitly what this number is. It's the GCD of the order of SP2G over FL for all L greater than or equal to 3. So this kind of number is something you see if you, for instance, try to bound the order of a finite group of integer matrices. One way to do it is by mapping that group, reducing modulo various primes, and seeing that you have to inject into at least when L is sufficiently large. This GCD actually doesn't change if you take L large. That's one way to control the order of this group. But it turns out that that bound is not sharp for a certain P. Namely Fermat primes, which sounds like a very small number of them, but of course it includes the friendly primes 2, 3, and 5, which have a huge effect on the order. So for instance, if you look at the bound so for G equals 2, for instance, the Silverberg prediction is 2 to the 8 times 3 squared times 5, whereas I already showed you what the correct answer is. It's 48. It's 2 to the 4 times 3 times no 5. So the 5 is entirely missing, and so one thing we can explain in general is why 2, 3, and 5, and 17 eventually, behave differently than other primes when you do this. So for example, when you get to G equals 3, we still don't expect to see a 5, but we do expect to see the prime 7, which you might expect because you can take the Klein quartic, which has 168 automorphisms, and twist by that and get this to have a 7 in it. But it's just somehow interpretation in terms of these motivic Galois groups, rather than just looking at, for instance, the action of endomorphism on torsion points, which is where Alice got this bound from. That lets you get a bound that's closer to the truth. It doesn't quite tell you what's going on at p equals 2. P equals 2 is a big mess. But at least for 3 and 5, we think we understand why those primes don't show up as much as you expect, but this is still a work in progress, so I don't want to make a formal statement. We'll stop there.
Are there any questions for?
So, if I give you an abelian surface over Q, can you decide in which one of the 51 cases it is algorithmically?
Well, 52, because the generic case accounts. So if I take an abelian surface over Q, can I tell algorithmically which case it's in? In principle, I think the answer is yes. What you need to do is compute the endomorphism ring of A over Q bar, and at least in principle, I think one can do that. Drew would know better than me what the status of that is. In principle, one can do that, right?
Yeah, and actually in practice now, that's very recent work, but yes, you can.
Okay, and so when you take the endomorphism ring over Q of A over Q bar, that's a Z algebra. You tensor with R, and essentially that R algebra plus the action of Galois on it determines the Sato-Tate group. And then we have that table. You can look up in the table in our paper how that correspondence goes. So yeah, it actually turns out to be something you can read off explicitly. Before you could do it explicitly, what we were doing was we were looking at these pictures to figure out which group we were hitting, and then sort of then checking after the fact that it matched. But you can actually now do it completely directly. I should say the pictures, of course, were very helpful in discovering what the correct classification was. It's much easier to prove a theorem when you have numerical data that suggests that you're proving the right theorem and not missing a case. The first few times we tried to do this, we were missing cases. So the data is important.
Yeah, from a practical perspective, the fastest way to get the classification you're asking about is to compute the picture. Don't look at the picture, but look at the moments, and those will tell you. But we do now have the ability to algebra. We have an algorithm that will algebraically prove that we've got the correct Sato-Tate group. But that was done well after the work that Kiran is talking about.
Yeah, these numbers are very, even for genus 2 curves, these are very efficient to compute. And in fact, progress is being made all the time on computing zeta functions of even more general varieties, even higher dimensional varieties. These moments along the bottom are converging to integers, and they're telling you something about the representation theory of the Sato-Tate group. They're telling you character multiplicities. And so, from an experimental point of view, the easiest way to sort of sort these things by type is to look at these pictures, but look at the moments really. But you can actually rigorously do it as well.
Is there a concrete example where the naive motif doesn't work?
Oh, that's an excellent question. Is there a concrete example where the motivic Galois group differs from the naive Galois group? The catch is in the word concrete. So Mumford gave a general construction of these things as complex algebraic varieties, but not in terms of equations, in terms of sort of points in the moduli space. And so I think we know for dimensional reasons, we know that there should be Jacobians of genus 4 curves that show up in this Mumford locus. But as far as I know, we don't know a single explicit example. In particular, we don't know whether you can find any examples over the rational numbers. Maybe somebody else in the room has a better guess about this than me. But as far as I know, we don't know whether these exotic examples can occur over Q or other small degree number fields. Very recently, progress has been made on computing, say, Jacobians of higher genus curves. So we could actually try to do numerical experiments to fish out possible candidates. But this hasn't been attempted yet.
Can you say something about how the classification of the 51 special types goes? Is it sort of the constraint from M naive?
Yeah, you take that, right. So in this case, we know M is M naive. So you use, there are some group theoretic constraints on M naive For example, there's one coming from Hodge theory, which says that there has to be a torus of a certain shape sitting inside here. And there's also the constraint coming from the fact that it's a group defined over the rational numbers. So that puts very strong restrictions on how it can, and with sort of enough Q rational points. That puts very strong restrictions on where it can sit. It is analogous to classifying, finite subgroups of, GL2Z or something like that. It's a little bit trickier because these groups have a positive dimensional algebraic component, but it's the same general flavor.
Any other questions?
Yeah, can you give an example of this one of the curves of genus things is bounded for the
Okay, genus 2?
Yeah.
This one right I have on the slide is an example. Yeah, the Galois group is is S4 across D mod 2. I forget, there are not a large number of these. I forget, are there a finite number of Q-bar isomorphism classes? Does Drew or Frances remember? Do we
Yeah,
know?
I think we over Q we can prove these.
Okay, so there are very few Q-bar isomorphism classes of these things, but they do exist.